at the company about 10 years ago. So today the goal is all the slides I've already shared with you. Like I think with Amy, I think so you don't have to take any notes. Everything will be there. So the goal is to empower you all to use to do the subsurface modeling, and also to leverage the power of AI, which will complement your expertise. And then we'll focus on the implementation, how we actually do it, which is how we load the data. I'll show you all the steps. And then we look at the subsurface risk assessment, like when you're prospecting a well. So I've taken one use case. There could be many other subsurface use cases, but the goal was to see how do we do a quick prospect using all the AI tools. It is not replacing the existing scientific model. It's basically augmenting that. How do we take those models and apply AI with all the geospatial information that it can provide quickly? And then we will be providing the software access 60 days for free. So once you send the logins, we'll send you by email. So you'll have access, and then we can have. So instead of showing you how to actually do it, there is also all the videos in the software itself. So you don't have to really take notes right now. But the idea is every week, we'll have a 1 hour session with you. If you want to have any help on the software. And then eventually the goal is, like if you want to do any collaborative projects, we can work with you, right?
Sashi,
Yeah.
did you share your screen to Google?
Oh, through Google, oh, sorry. Oh, I forgot to share, yeah, my mistake, yeah. Yeah. Yeah, and also the goal is so we have a very strategic partnership with Amazon Web Services. So our objective is to load up the entire public data that's there in the world, essentially. So we have been doing a lot of work in Brazil, loading up all their data from their national ANP website. Now we are looking at India. We are looking at Malaysia. So we are loading up all the subsurface data that is publicly available. And the idea is when you're training for AI, you'll be able to load up all this information and you can leverage some of the existing data. And then you can also bring in the proprietary data. That's when you'll have the operator give you a dedicated workspace in the platform. And you can load up the proprietary data and do further modeling. But you'll have all the public data that is loaded up into the platform, right? So it's been a constant exercise for us in the last 2 years. We finished up the Brazil, now we are loading up other kinds of data sets. So one of the goals was to load up all the publicly available data in the Anadarko Basin, Permian Basin, whatever is publicly available that we want to load up. And we don't have direct access since you have a lot of experience. So if you can, collectively, we can load up the public data, that'll be good. And we'll help you with the tool. The idea is the platform will have the public data, you'll have it freely accessible. And when you actually want to do the modeling, that's when you can leverage that and you can work on a specialized project with the operators, right? That is the whole idea with this approach. And then, so this is the course outline. So I'll briefly talk about what Amazon is planning to offer in terms of the cloud architecture, how we can scale. So there is no software installation. It's all on the browser. It's all on the web. So all the loading up, everything is on the web. So all we need is, so after today, you'll get an email login access, so you can use the software for there. So Amazon, we have a strategic partnership with Amazon, and they provide more or less the compute and the infrastructure for us. So we can load up everything into the cloud. So for example, we are loading up a lot of seismic data from the Brazilian fields. They have close to about close to a petabyte of seismic data, out of which about 300 terabytes is more public. remaining is all proprietary. So that kind of data is all loaded up. And pretty much all the publicly available data from USGS, all of that we are constantly loading into the platform. Same thing with the well logs. So ANP website in Brazil has published all the data. So we are also loading data from the Canadian websites as well, because there you have to publish some of the data sets. So one thing what I wanted to understand is with respect to Oklahoma and also Texas from the Texas Railroad Commission, how much of the data we can load it into the platform. Again, the well headers, all that we need to look into that. But the idea is once you load up into the platform, then you all will have access and you can work on it. So, and then I'll also explain the agentic framework that the tools that AWS already provides. And then we will go through how we load up the data. You all might be familiar what is called OSDU, Open Subsurface Data Universe. So that is a new standard that the energy companies have come together to define a universal standard for loading up the data. Basically, Chevron, Exxon, Shell, Total, BP, they've all come together and they've created this platform called OSDU. So that gives you the framework of how you store a well log, how you store a trajectory, how you store a core data, all of that, including seismic and all that. So that is part of the OSDU framework. So this platform supports that. So that means if you have a well record from Oklahoma and well record from Texas, you can come up with a universal standard. So that's what the platform is doing. And then we have our software tools that can help you analyze the data. So, and then we will show you how to integrate the data and the seismic ingestion, also the geobodies. And the last part is how do we do the prospect suitability model within the Anadarko Basin. So I just took one example. And this is an evolving approach. So the goal is not to replace the existing subsurface modeling techniques. You take that and you take all the different economics into account. And the goal is to do a quick analysis of where do you look for that, right? So it gives you a quick suitability model. Like if I want to drill a well, then it goes through a bunch of criteria, which I'll go through today. And it'll say for this prospecting well, is it a go or no go? So based on certain criteria. Now, then you'll go in more detailed analysis. So that way you can model hundreds of what if scenarios and work on that. So that was the whole idea with the prospecting. So just to give you a background of who we are, essentially we are based out of Houston. We have a data center in Bangalore, so where we manage a lot of the Middle East operations and also Far East. We are a partner with AWS, so AWS has an investment in us in terms of scientific data management, and then we work. Basically, we have like 4 patents on how we manage the data, and then I'll go through some of the analytical approaches as well as how there is also a lot of on-prem data that we are processing right now from tapes, the seismic data that many companies have. So that is another area that we are actively working on. So the main approach is mainly we are in the upstream. We have some in the pipelines midstream. We are actively working in the geothermal space where we are doing continuous monitoring. And also the industrial automation where we are doing a lot of real-time data from sensors and fiber optics. Just a quick intro, as she told you, I'm a TU grad. So I've been primarily working in the geomechanics and also the subsurface modeling. I was one of the main architects for the Jewel Suite software platform that Baker Hughes has. And about 10 years ago, we started Petrabytes. And since then, we have been heavily involved in the modeling. Yeah, these are some of the products that we will go through as during the course. So essentially, we have a data management platform as well as an analytics platform. Right now, what is happening these days is because the data is all over the place. Some software systems have, like for example, BP has a software platform that defines a well record in a specific way compared to other systems, right? So then we have to connect to those systems to pull the data. So a lot of different various systems are there, and that's why we need all these connectors that can pull the data from different sources. So our software works like the hub. Like Shell has their own definition of their well records, their system of records, right? So same thing with TGS. So TGS has a what is called a dataverse, which has all the well records and also all their seismic data. So we are able to connect to them and also pull the data from that. So this was a cartoon, like you all probably are using like a CRM tool. Like for example, HubSpot is one of the most widely used the CRM tool. And this was a cartoon they suggested, how does the future of work look like? So you'll have SMEs, you'll have data scientists, and you'll have agents, and you'll have DevOps who will be integrating that. So that is how they're looking at some of the future of how your newer workforce will look like. And I'll show you today some of the examples of how you can create agents, and the agents will be able to do a lot of work, like for example, reading data from PDF files, extracting metadata, those kind of things. So a lot of things that were not possible before, now you can automate that, and then you as an SME will be able to put it all together. The reason why I put this slide is we are doing a lot of digitization of the really old data, like from TIFF images, from really old scanned images. Today, I'll show you an example. So we are taking data from images, we are taking data from text, and the audio is mainly for the fiber optic data where we are listening for sound. Let us say you're drilling a well and you're looking for any kind of casing integrity. So we are able to take the data from sound and also have that model interpret what kind of wellbore event it is, right? So that is one of the areas why how we are leveraging the newer AI models and the OCR models to further accelerate the data processing. As you can see in the last 2 years, right? The moment ChatGPT came in, now with Claude, a lot of automation has come in. So we are leveraging a lot of automation. So for example, I'll show you a simple workflow of the well logs and also the seismic, how we are able to quickly parse the data and populate all of that. So this is happening as we speak, where there's a lot of automation being done, especially in like in the data processing world, and even on the interpretation side. So for example, if you say, what does 20,000 PSI of rock strength mean? So AI can answer those questions instead of saying it's a shaly sand or a weak sand. So it can give you those kind of interpretation questions. That way, when you're analyzing the data, you have all the information handy and you can make a decision. So it's not going to replace what you're trying to do, but it gives you a lot of information. And all these models are trained on the knowledge graph. So what we are doing is a basin by basin, we are bringing the knowledge graph. Like for example, we have like a knowledge graph for Anadarko Basin that looks at all the history, all the reports. And so knowledge graph is essentially, it takes all the data that you have and it creates a searchable index. For example, what are all the plays? What are the primary areas of production? What are the drilling problems? All of that is automatically indexed. So when you do a query on that, it'll give you like what is the porosity distribution, right? Based on that, it can give you an outlier whether this is. So that will help in digitizing the data, all of that. So all these are additional information that is available handy with the knowledge graph. So that's what the AI is providing. So which previously you were actually searching for information in order to QC and all of that, right? So that is one of the key acceleration that we are seeing using AI. Okay, so I will jump into each aspect and you can stop me anytime. Again, all of this information, I'll share this with you. So first up, let's go to the subsurface model, what AI provides, what AWS is providing, right? So first thing is they provide lot of compute. For example, we are able to load about 3 terabytes of data in less than 2 hours. into the system. We are able to process all the data in distributed computing environment, right? So that's one of the key areas that the cloud is providing. So AWS has the stack. You can scale, like I can run multiple processes at once, and we can process all the data. I can take all the segway files and extract all the information and ingest the data into the repository. Same thing with well logs or any kind of alerts. So let us say you have 5,000 records or 5,000 TIFF files. That gives you that scale. So I'm able to quickly spin off new computers or new compute clusters. So that's what AWS provides. The second thing is it provides what is called enterprise AI framework, which is a lot of the challenges when people are asking questions with ChatGPT, there is a concern that it is training on your questions and all of that, right? So AWS provides that closed loop where the models are not training based on what you do. It's a pre-canned environment, so it's a highly secure. It has all the guardrails, so it creates that enterprise AI framework on top of the compute. And then once you have that, it is pay as you go. So let us say you process 3 terabytes of seismic and you want to scale down, it scales down. So it's pay as you go. So that is how you can quickly bring up the scale up of the compute and also the AI framework, and then you can scale down. So that is one of the key advantages with the cloud, with what AWS is providing. And then there is a whole bunch of AI tools that it provides. So for example, you all probably are using Claude, Workspace, all of that, right? So now that is also integrated as part of the AWS ecosystem. So some of the things which I'll be showing you today, it's using the Claude model from Anthropic, and that is all packaged by the AWS cloud framework. So in essence, what AWS is providing as a cloud platform is it provides the infinite compute, that's what they say. So you can add as many computers as you want. And then it gives you the enterprise AI, a secure enterprise AI with all the guardrails that prevents anybody from misusing the data that you're giving in. And so that is how it's leveraging all the different models. The other thing what it also provides is, so every day, if you look at the Hugging Face, I don't know if you're familiar with the Hugging Face. So Hugging Face is the open source or the repository where all the new models are coming up. So for example, if you have a new OCR, there are a bunch of models that are provided in the Hugging Face. So people are building a lot of new models. There are close to 2 million models right now in the Hugging Face. And all of it, what you can leverage and process the data. So what AWS is doing is it's providing a secure framework to use that information. That way, nobody's training off your data. Okay. And then you have a whole bunch of, they call it what is called a bedrock, which is basically the foundation for all your AI models, and it provides you all the tools. Okay. Behind the scenes, this is the technology. So basically, they have the bedrock, they have the step function. So some of these are, some of these tools are, you can treat it as automation tools. Like for example, the Lambda functions are something that you can trigger. So for example, we were doing one of the projects for Shell where as soon as the data arrives, they want to process the data. So all these are automatic triggers that you can have into the software. And then you have this whole process for which I will go through today, this aspect of data ingestion, data processing, all of these things. There are specific tools, like basically it's a framework and then you can build on top of it, okay? At a very high level, to summarize this, it gives you a open framework where you can scale as you go, and you don't have to again. So previously what used to happen is like if you see a lot of the seismic processing companies, right, they used to have a floor like this where they have a lot of computers and tapes and all of that, right? That's how now all of this is migrated to the cloud. So there is, you can quickly add more scale, right? For example, right now we are working with Petrabytes. They have 3 petabytes of seismic that is being ingested into the platform right now. Of course, they're going to ingest over the next 2 years. That is their active field. But they have a whole bunch of legacy data, like non-active seismic data that's close to 60 petabytes. So all of the data is being aggregated here. Now, TGS, the geophysical company, so they have close to 100 petabytes of seismic data. And they're all running in the AWS cloud. So that is the scale of the data that is being processed in the platform. So are you following what I'm trying to build the foundation just to give you an introduction of how the AWS ecosystem is, and then we'll go deeper into each model. Is this space is the way I'm explaining, is it good enough, or is it too more on that? So I'm trying to keep it at a very high level. Technically, when you're using the platform, you don't have to know any of these. But what is increasingly happening is these tools are pretty straightforward to use. Like anybody, you can easily generate code with these tools, like for all of that. So I see we have a lot of high school graduates that are leveraging these tools to process a lot of the data, right? So it's pretty easy to use. But what I'm trying to say is, irrespective of our software, these are the tools you can leverage that AWS has provided, a lot of tools. Okay.
Question.
Yeah.
I think these no terabytes from seismic data. How large is it petabytes? Is it 1,000 terabytes?
Yeah, 1,000 terabytes. Yeah.
1,000?
Yeah. So TGS, they have a new kind of mapping the sea right now. So they have, they're collecting a lot of offshore data. We are also working with a company called Archer Well Services. It's a Norwegian company. So they are doing vertical seismic profiling. So essentially, it's a near wellbore seismic where they put a fiber optic cable and you're getting every meter, every foot, a pulse. So essentially, you're getting sound measurements close to the wellbore. So what they're doing is they're monitoring the well for the life of the well. So every day generates close to a terabyte, the actual amplitude. We do a lot of processing on-prem next to the site. So that is slowly being used as a replacement for seismic. So typically people used to do 4D seismic. So they do a log here, and then after 2 years, they'll have another seismic acquisition, right? But now with fiber optics, this company actually puts a cable in the casing, like in the production after the completions, and it's continuously logging the data. Okay, it's exactly like how you see, it's basically vertical seismic profiling. So what are they looking for, right? So a couple of use cases, what we are doing right now is for leak detection, and also in all the shale plays, we are looking for the fracture propagation. So it gives you, because of the sound, it shows you where the fractures are being propagated continuously. So they log the well for 1.5 days, they collect the data, and they can see the fracture propagation. Okay. And all of this is possible because I can add easily more and more compute into the cloud. So they estimate close to 5 petabytes in the next 3 years of gathering. So every month they're getting 50 terabytes of seismic data. Okay, so. I'll briefly talk about OSDU. There is a lot of literature online, but I just want to quickly summarize. So what is an OSDU platform, right? Yeah.
Just real quick, maybe I'm confusing computer processing with like seismic processing. So is this processing the actual seismic data?
Yeah.
So you're kind of cutting off that function.
Yeah. And I mean, yeah, of course, seismic processing is a wide range, right? Ultimately, what they're doing is they're trying to get the seismic attributes, right, to characterize mainly the drilling risk, right, or the potential pay zone. And a lot of companies are doing machine learning to identify the geobodies, like where exactly is the fault, right? And that is what is accelerating at a very rapid pace. So previously, they used to take 3 months to detect the horizon and all of that. It's usually a geophysicist is picking something, and there is another geophysicist that will say it's off by something, right? So now all of that is being accelerated with the machine learning. Now we'll go a little bit more into that. So TGS, so now we are working with TGS to create what is called a well log foundation model. So just like how you have ChatGPT, all of them, as a model that is trained on all the public knowledge, right? So we are building a small language model, which is very specific to well logs. That means, so for example, if you're doing depth stretching, right? The foundation model will give you, if you put a prospect well, where exactly the, like what is the formation tops along that, or the well logs, right? So just like how you ask ChatGPT for like any kind of information, now this small language model is trained on specific well logs. Again, it's a regional based also. So for example, what the model you get in Anadarko Basin will be different than what you see in the Permian Basin. So it'll be very sensitive, right? So that is where a lot of training is required. Yeah.
Do you have the option to see that data?
Yeah. Yeah. So again, there is a whole bunch of algorithms that we are working on continuously optimizing. Lot of the simple heavy lifting is done. So for example, if you say, what is my bulk density, right? You know, all the data should be between 1 and 5 gram per cc. So it'll automatically remove the outliers. So all those basic stuff is easily eliminated very quickly. The more deeper QC is when you say, my total depth of the well, my formation tops, well tops should be less than the total depth of the well, right? So that is when you are looking at multiple things. So those are the advanced ones that also can be trained, but you have to create a template, right? So yeah, I'll go through the whole ingestion process, how we do that. But so that is where AI can be really helpful, right? Where a lot of the mundane things can really accelerate. And the good thing is, even on the interpretation side, like if you're a novice, if somebody is starting off a job, he can get a 50% answer very quickly by understanding, like, what does breakout mean? What does washout mean? All of that is readily available with the AI tools, right? So it can give you, it has all the peripheral knowledge that it can quickly feed, right? So that is how most of the productivity gain is time savers, right? The actual interpretation is still left to you. Like, for example, all these productivity gains, is it helping you in discovering new fields? That is a big question mark, right? Or is it helping you mitigate any of the drilling risk? That is a big question mark. But definitely you're able to have measurable speed in computation or faster interpretation. That's where you're able to really quantify that. Okay. So I'll quickly explain what OSDU is. So about 7 years ago, Shell, Exxon, Chevron, BP, and Total, and AWS, they all came together and they said, we need to create a standard because there are so many vendors, so many issues with seismic, so many issues with data, with coordinate reference systems, all of that. We want to create one universal standard of storing the data and also exchanging the data. So previously there were many standards like POSC, PPDM, all of those things, right? But they were only defining the standards, but not the implementation. Now, OSDU is the one that is actually defining an implementation. And they said it will be cloud only, it will be a cloud-based solution. So then you have Microsoft, Google, Amazon, they're all part of this ecosystem, right? So that is where we partnered with AWS. So now the way we store the data is a universal standard. So Exxon, for example, Exxon is mandating all software vendors to use the OSDU standard to manage the subsurface data. You will still have the LAS files, DLIS files, all of that, but they're all migrated into cloud-based standard. So that's what OSDU is providing. So it has a core services. Like, for example, if you query for a well log, it gives you a metadata in a JSON format that is easily consumable by all the web applications. And it will give you all the depth-based thing, except that it is not stored in a LAS format. It is stored in a different format. that is universally understood by, it's more cloud optimized. For example, Segway standard has been there for last 40 years or even longer than that, right? But it's very difficult to use. There is no standard, like if you see the Segway header, it's all over the place, right? So what they've done is they've created a new format called VDS, the volume data store. So Shell actually funded a company called Blueware to create this standard. So this is very cloud optimized, and when you query the data, it's much faster. So that is where they go from terabyte to petabyte scale. Now TGS, the geophysical company, they created what is called a MDIO format, which is multi-dimensional input IO format. It is similar to that. So they are storing all that seismic data converted into that. So where do we come in? We transform all the legacy data into those formats. And that is where we are working with all these companies, right? So same thing with Schlumberger, they have ZGY format, which is also cloud optimized. So all the petrol, all of the decision space, they all use ZGY. So to summarize, right? So all these big companies said we want to standardize the data, so that's what they did, the OSDU. But they also wanted people to actually implement, not just define a standard, which will take another 30 years to implement that, right? So that's when the cloud people came in, and that's where the acceleration came. And the biggest thing was they wanted the data to be AI ready, to apply AI, right? So now these formats, they're readily be accessible to perform any kind of AI based applications. Now, that is where if you see some of the Silicon Valley companies like Databricks and Snowflake, you would have heard of them. So Databricks is one of the probably the next IPO. So they are also actively working in the energy space because now the data is ready for AI. So they're writing all the agents and all of that. So that's where all the tech companies are now heavily involved in the subsurface domain, along with all the major players, right? So that is how it is rapidly evolving, the landscape of the data processing and the interpretation, all of that. So essentially, you will see, as I said, like the future of work will be like geologists like you all combined with these agents and all, it will be all cloud-based. And it's moving at a much rapid pace. So now, where are we with this OSDU journey, right? So Petrobras, Shell, Oxy, Chevron, BP, ConocoPhillips, Total, Equinor, Aker BP, Petronas. So these are all the companies that are actively adopting this, right? So, and there are more than 230 member companies that are actively working on this, right? So we also started working in the mining space. So BHP Billiton, Rio Tinto, they're all in the mining space. So we are taking this and applying the same standard for mining. Because if you really look at it, it's all shallow, right? They also have horizons. They have drill holes instead of wells, which is like 300 feet, 400 feet, right? They have lithology. They're looking for critical minerals, the distribution, just like any other lithology. So it's strikingly similar domain. So we actually adopted this for mining. So we created the dictionary, everything, like the terminology, all of that. So it is also rapidly evolving. So the OSDU standard, like a lot of donations came in. So PPDM donated that. Energistic standards have donated that. POSC, which was the original system, like almost 40 years ago, that defined the unit system, is all part of OSDU. So it's not something that started from scratch. All the standards have converged, except the big difference is the implementation. Like how do we actually implement this standard is all given by OSDU. And that's where all the cloud providers are there. Okay, so like for example, they're running the seismic inversion right now in the AWS cloud as part of this workflow, right? So, so many of them, I think I would say in the next 2-3 years, you'll see rapid adoption of OSDU. and also the agentic AI. You'll see many more agents coming up. People are actively working on agents for mainly, as I said, like to accelerate any regular work. There is still a question on the interpretation, how much of interpretation you can do. But the gap is reducing because if you have, it's like I'm a doctor, I have like 10 critical patients and I have all the vitals, everything information right at my hand, they can make a decision, right? So that's where AI is coming into play. Same thing with the subsurface. You literally have pretty much every information that you can provide quickly, and then you make a decision. So what we do is, so this is where our PIEScale, which is the platform. So we have, so typically what happens is there are a lot of desktop softwares like proprietary workflows, right? So Kubernetes is a technology that is meant for distributed computing. So for example, if you go to AMC theater, right? If you have only one counter and you have 1,000 people, so that is slow. If you have like 5 counters, you're processing multiple at the same time. That is the same analogy that you have for Kubernetes. So if you have like, say, I have like 1,000 Segway files, I can run in parallel. If I have like 10,000 well logs, I can run in parallel. So it scales automatically. So that is the whole idea with the Kubernetes. Now, let us say you're doing well modeling, right? So when you're doing well modeling, let us say you want to do nodal analysis, like production allocation of all of these. So you can run all this in parallel, right? So that is the whole idea of the Kubernetes platform. Now, this Kubernetes is running in each of the cloud. So we run on AWS, we run on Microsoft Cloud. So they give you the compute. So previously, you had to spin off multiple desktops and things like that to add more and more compute. Now it's all in the cloud. So we scale it and you specify the configuration and you go from there. And as you're running, so let us say today you have 10 logs, tomorrow you have 1,000 logs, you can scale automatically. The software is the same. So that is the whole idea. So these are all the different subsurface data we process in the cloud, in our platform. So take, at the subsurface level, right? So you have the field level, right? You have the reservoir grids, you have horizons, you have faults, you have all the geobodies. And then as the well is being drilled, you have the real-time data, like with SML data, all of that. And then once the well is being completed, you have all the completion information, you have the thin sections, the core samples, and all of that. And then when you're monitoring the well, that is where you have the DTS, distributed temperature sensing and acoustic sensing. You're monitoring the well. So we take all of this into account. And the beauty is OSDU supports all of this. So there is a standard for each one of them, right? They have defined schemas. Now, who is defining the schema? The community. So you have people from Petrobras, we have people from Exxon. So for example, Exxon has donated a schema for rock and fluids to standardize all the petrophysical and rock and fluids data. So few petrophysicists from Exxon, they have created these standards. Like basically when I say standard, it's basically a schema of how you represent the data. Like for example, water saturation. How do you determine that? Like gas oil ratio, right? So all those are basically they're defining a schema, like a standard for that. And every other software has to conform to that, right? They don't want their own proprietary format so that other software cannot read. So they're removing that barrier. So that means like if Petrel is the software and OpenWorks is the software, they both should be talking to each other with the same standard. Right? So that is the whole idea. So it's more like a Google Translate, right? If I'm speaking in French and you're understanding in Spanish, with English as a primary language. So OSDU is like English as a primary language, right? So that's what they're defining as a standard. And it is adopting, like many companies are adopting very quickly, right? Especially in Europe, you see Equinor, Aker BP, they're very aggressive in this because what it is enabling them is to do AI workloads. So if everything is standard, then you can leverage Claude to use that. So that is the whole idea with these standards, right? So this is our platform. So if you look at what it does is it has a data lineage. So for example, where did the data come from? Did it come from a report? Did it come from data, or was it processed a couple of times? So it has all that lineage, right? And then as you're ingesting the data, it looks at the data quality. So I'll show you an example of seismic and a well log. Like for example, before you do any kind of inversion, what people want to do is how good the data quality is, right? So they want to take all your seismic files, and the AI models will run, look at all the headers and say, they'll give you a score based on certain criteria, which I'll show you in a minute. And based on that, it'll say how good the data is, right? Before you do any further processing. Then you go back to the vendor or correct it, or you denoise it or fix the header and so on, right? So that is the whole idea with this approach. And then we have a whole bunch of data pipelines, which is basically, let us say you have 10,000 well logs, we can ingest all of that. Like for example, we were doing a project with OXI, where they had about 5,000 documents, like TIFF files, PDF files, and all that. We had to extract all that information and ingest into the platform, right? So that is all of this. They also have what is called reference data. So reference data is like if you work for a bigger company, they have all these standards, the units, the codes, the department codes, like what type of data it is. Is it interval velocity or a root mean square velocity? They have all these definitions that is well defined, right? So that is the reference data. So that way, when you use the same terminology across all the software. So that is one area, even though it seems very fundamental, that is where the incompatibility comes into play. When one software doesn't talk to each other, to other software, is because of that. So there's a lot of emphasis on that. And there is also a lot of metadata that is generated. So that means for every well, there is a header. What kind of coordinate reference system it is? Is it NAT27, all of that? And what kind of conversion you are using? Is it WSG84? All of that. So there is a very strict CRS coordinate reference system. They are called geospatial consumption zone that is well defined. So all that complexity that you had spent time, like locating the well, missing units, missing headers, all of that is being resolved in the system, right? And you do a QC and it'll give you a score on that. So let us say you get some data from your from any of these well headers, and you have the units that is missing, right? So then you don't know whether it's from the US or from Middle East or some other place. So then you have a location problem, right? So immediately it will flag all those things, right? So by the time it goes into the system of records, you can trust the data to do any kind of further evaluation, right? And that is the whole ingestion pipeline, which I'll walk you through of how we ingest the data. And then because all the metadata is nicely organized, now I can search. I can say, give me all the triple combo logs from Eddy County. Because I have all the metadata, I can do all those kind of things. And then we have the metrics, and they have what is called a persistent collection. So let us say you're analyzing a specific play. You can take that data and you can basically bookmark kind of thing, and you can share that persistent collection to somebody else for further analysis. So that way, from thousands of records, you're taking a small subset and you're marking it. It's like an encapsulation of your project with all the metadata, right? So even though it sounds, very basic, but the industry has been struggling to do that. Right? That is the reason why they created this whole OSDU standard to solve a long-standing problem in a different way with the new set of tools, and also using the cloud and AI, right? So that's what they're using. Now, at the end of the day, they create one unified data set where everybody, all the softwares are accessing the same data in the same way, right? Like if I'm the software that is compatible with OSDU, there is only one way of accessing the data. So other software use the same API, they'll get the same record. So they're avoiding data duplication and also non-conforming issues. So everything is conformed to a standard, right? So for example, right now, for for Occidental Petroleum, to give an example, we ingested seismic data into the platform, right? We converted the data, we converted into seismic attributes, everything. And Petrel, the SLB software, was able to pick it up as it is without any change, right? Now, we both are not talking to each other, we are talking to the same system of record. So that is the advantage. And the same thing, Halliburton software is able to talk to the same OSDU without worrying about this one, right? Now, how does it impact small players like us, right? So we are also conforming to the same platform. So now we can compete with the big boys, with the geologists, and we can offer better services, those kind of things. So it is creating more like a level playing ground of when you create a standard, many new things will come out. Because most of the time, if you don't have access to data, you can't do much, even though you have the expertise, right? Now, with the standardized approach, as long as the operator is willing to give you the data, you can now operate, right? So you see, this group has 230 companies all working together. So imagine how much software is being developed with agents and all of that, right? So the standard is opening up. So Equinor donated their wall field. It's like 50,000. It's 50 million barrels of oil. I think the field is shut down, but it gave that data set was actually used to develop the OSDU standard. So they donated the data with all the seismic data, well logs, core samples, everything. And if you see, most of the OSDU was actually developed through the wall field. And there is also Groningen out of Netherlands. So they also donated the data. So we work with the Norwegian agency, the government. It's called Discos. So they have opened up 50 years of data now. 50 years of the Norwegian data, pretty much the existence of the Norwegian field, right? So all of the data is now exposed to the public. You still have to pay a fee or something like that, but it's ready for interpretation. And what they're trying to do is, because it's heavily offshore, they want to mitigate the risk. So they're asking software companies to build on it, to build more AI, and Aker BP is hiring a lot of AI engineers to accelerate that whole. They want to do autonomous drilling, all kinds of things, right? So the trend is, the more you standardize, the more you put it in the cloud, you have easy access, faster processing, and you have the ability to scale, and the AI is only accelerating. So that is where the whole thing is moving in this direction. Now, from our standpoint, so AWS has a software called Energy Data Insights. So behind the scenes is our engine that is running. So that is the reason why I'm saying, like, we have a good mandate to take pretty much entire US data, put it in the cloud, and do all kinds of things. And AWS is fully supportive of it. In fact, some of the data is already there, available in the AWS cloud. So anybody can grab it and start working on it. Like, and they can build agents on that, right? Now, we as a company, we work very closely with AWS, and we are constantly, upgrading all the public data. So one of the things we were actually thinking is, like, mainly target, say, for example, Oklahoma and Texas. If you have any of the public data, we can load it, but we need your help to do the QC, right? The software can do many things. Probably it can do 70% of it, but then you want to do the final 30% and do the QC, right? Now, what will this help is, in the bigger context, if you want to build AI models, you need a lot of data. More public data you have, the better it is. For example, ANP, which is the Brazilian national agency that looks at all the seismic, they have close to, for example, 13,000 DLIS files with all the well logs. And they have all the core samples, right? We have digitized all of that, and it's there in the platform, right? So the more we have, like, for example, Trinidad, we are looking at the Caribbean, so they have national repositories, and we are populating all of that. So the more data you have, you can build a pseudo model, and then when you have the actual data, then you can build on top of it, right? Then you can say, this is my proprietary well, which the companies will not expose that, but then you can offer it as a consulting service to analyze the data, right? And your regional experience will help. So that is what we're trying to do, right? So for example, we are working with one company that has data from close to 500,000 wells gathered over last 40 years. They're still digitizing a lot of the data. There's still really old logs from TIFF files. They're still digitizing that. And we are helping them in the last mile of digitizing that whole effort. So, so that is where it is, right? Now, whatever we do in AWS, same thing. Microsoft is also pretty big on that. So they also have that. So yeah, so everybody is adapting in this journey, right? Another example is, I'm trying to explain so that you all can think of where you can apply this whole technique, right? For example, the Willow field that ConocoPhillips is developing, right? It's a $9 billion asset that they're building right now. I think they're going to spud in 2027, right? So they're trying to build the common data platform for the Willow asset. So they have like 37 wells that are constantly monitoring, like I think it's like Wildcat wells. They have the whole workflow, all the way from geosteering to well testing to geoscience to fiber optics to well to production, all of that, right, in one common workflow. So we have been actively working with them to create that common data platform, right? And they have a whole bunch of vendor softwares. There are like close to 32 vendor software that they want to use. Now imagine the whole effort, right? And this fiber itself is they're collecting about 300 terabytes, 200 to 300 terabytes a month, right? So they have a whole bunch of problems, and the companies like us are helping them to digitize that and populate all that information. And not only digitize, like it's a continuous loop, right? So as the geosteering is giving the new depth, new trajectory, the system has to update, right? And the other software has to pick it up. So that means right now we are connecting with Roji software, which is the geosteering software. And then we are updating the seismic profiles. We are updating the well testing, all of that. So that's a fully closed loop approach, right? So, and the same thing for Oxy, right? Oxy has close to 60 petabytes of seismic data, right? And they have close to 30 million records, 30 million well logs from all over the world, right? So they want to put all these systems into account, right? And obvious problem which you can always correlate, right? They're always struggling to find the data, right? This has been a decades-old problem, and we are still having the same problem, and this is alleviating that problem, right? So, these are is the same technology, but as I said, like the Silicon Valley companies like Databricks, they're also part of this, and we leverage their compute, right? Just to give you a brief, like 1 minute intro of Databricks, right? So Databricks is a platform that is being used almost every industry, like finance, logistics, healthcare, everywhere they're using it. And now energy companies are actively adopting that. So it's a cloud-based platform that can scale and do a lot of processing, and it's AI-ready platform, right? So now all the major oil companies like Shell, Chevron, Exxon, they're all adopting that. And our PIEScale can also connect to that and interact with it with that platform, okay? Again, the same orchestration with that, okay? Do you want to take like a 5-minute break? So is this a right approach? I want to give a foundation, and then we'll go through the software in the second half. And then, as I said, like later on, we'll give you the software. I didn't want you guys to keep clicking the software, but understand it. Again, it's a 60-day, you'll have access to the software, right? So all that, the software has videos and all that, how to do it. There's a lot of public data. Like our goal was to just give you the background of the philosophy of why we are doing it this way compared to the existing.
I think an example would be really helpful.
Yeah.
But so you're more providing data platform. So
Data platform plus algorithm.
and then you'll go into the implementation part. Okay.
So if you look at any chat GPT or any of this, right, the user asks a query and there are a bunch of agents that is trained on the knowledge. Like for example, if you ask questions about nuclear fusion, there is a knowledge base that it's trained on, right? And then the cloud model will have a bunch of agents that is giving you the response, and they expose that. So if I want to use cloud model, right now in our system, we use the cloud model. So we can, or OpenAI, and they give you an API. So that means in your software, you can embed a call to cloud model that you won't see, and that's what you have. And then you have all the database and all of that, right? And then it's also can connect to multiple sources, documents, relational databases, and all of that, right? Just quickly, there are different kinds of agents, which is purely functional. Like for example, you want to send a weekly report, those things can do that. But if you want to ask specific questions, that is the knowledge base, right? So that is where you have the functional knowledge. So these are the two kinds of agents. So typically, most of the productivity, you get it here, like extracting text, right? So if you see the Gemini models are being used for all the legal documents, right? So what used to take months and days, they're leveraging using the tool, okay? So this is a very important logic, right? So essentially, a large language model is like a decision tree. So it basically says which agent to call, like whether if I'm asking questions about wells, it calls that agent. If I'm asking questions about seismic, it asks that. If I ask questions about the geobodies, it asks that, right? So it's a decision tree. There is a supervisor agent that is calling each one of them, right? I'll quickly skip all these things. So this is more like real-time streaming that we worked with Shell, mainly to get the real-time data from sensors. So probably we'll come to it later. I'll just skip through this. I'll spend just 1 minute in the context of Willow. Because of the data being gathered at the well site is so big, we are leveraging the edge computing. So that's what this slide is all about. Well, again, we'll come back to it later. Okay. So I'll just spend like 2 minutes and then we'll jump into the software. So essentially, the subsurface analysis is pretty very vast topic. Here we are showing you just one workflow that we adopted, mainly from the drilling point of view, right? So first thing is we compute all the rock properties and stresses from the 3D and 4D. We extract rock properties along geobodies and wells, and we do 4D seismic analysis. So essentially, we are looking at what is the variation of the 3D property, right? And what is your best path, and we are optimizing the trajectory. So that is the whole purpose of this workflow. And in drilling, we are mitigating the drilling risk, right, using the geomechanical model. So we look at all the horizontal stresses, vertical stresses, and we come up with a sequence of where the trajectory is, how good the trajectory is this the right path? We look at the stability of the well, right? That's what we're doing here. Completions, we host the Halliburton completions database, the intelligent completion. So our software is actually hosting, they have like 5,000 wells all over the world, intelligent completions. So we host their database of all the production packers, everything. Again, this is the fiber optic that we do the inflow modeling, all of that. Essentially, this is a steady state modeling. So what we do is, if you have a completion, we say how much flow you're getting from the sand phase, how much you're getting at the surface, and we do all the different kinds of what if scenarios. Like for example, as the reservoir pressure is decreasing, how does the flow change? So it's purely nodal analysis that we do from here, okay? And then this is where we are using the fiber optics to characterize the hydraulic fracturing. And then we do the zonal flow estimates with those sensing models. Okay. We'll get to it more detail. Again, all of this I will skip through. I'll come back to. So at this point, we'll just jump directly into the software.
You reshared and
Sorry?
you reshared and we get into the software.
Yeah. Oh, sorry. Yeah. So as I said, like by end of today, you all will get a login to the software. So we have some data loaded so you can play around with it, right? So right now, this is the OSDU platform. Like our software PIEScale is connecting to OSDU, which is the subsurface repository, and it's fetching all the metadata, right? I don't know. Yeah. So it has 262,000 well logs, curves. I don't know if you can read it. Yeah. It has all the perforations. It has the completions. It has about 26,000 documents, tubular assembly, well logs, all of that. Again, these are all random data that we have loaded just for you to get a sense for it, right? The good thing is it can load pretty much everything, like the geopolitical entries, all of those, the basins, the fields. So there is a structure for it, how you load it. So for example, from the Oklahoma website, we downloaded all the shale plays and everything from the USGS. So we loaded into the platform, right? So you can take a look at that. So let me just jump into this. So right now I'm opening a saved project. Okay. So right now it is fetching all the different fields. Okay, so it's taking a little bit of time. My Wi-Fi. So this is the Permian and this is your Anadarko Basin, right? So just to give you the background, right, how we loaded up, just to understand the standard, right? So if you click here, so this is the geopolitical entity. This is the standard that OSDU has defined. Okay, it's taking a little bit of time. Now, all of these, the coordinates and all of that, right? They're all well defined by the standard, right? So I'll go through the ingestion process. So essentially, let us say I take data from Kansas, I take data from, Texas Railroad Commission. They have their own naming convention, right? If you take Canada, they have their own naming convention for the wells, right? So you can all convert into a common domain with all the EPSG coordinates and all of that, right? So you're kind of standardizing the data. And this metadata, so when we say what is the standard, right? So this is the standard, right? Again, you don't have to see all this, but this is the standard. Again, behind the scenes, we are storing all this information, right? So just to give you a quick background, right? So they have the ID, which is a unique ID. They have the kind, which is a geopolitical entity. So all these schemas for every data type, like well completions, trajectories, formation tops, core samples, rock images, seismic, all of that are very well defined. All the schemas are well defined. So that's what over the last 6-7 years, all the operators have defined a standard. And now we are adapting that. Okay. So what you can do is, here is where you can look at, let me show, let's go to the metadata search. So now I can search for the wells here, right? And when you click on these wells, so for example, let me look at one of the wells here. So I'm searching for this well, right? So here I can look for which county it is. So it's in Eddy County. I have the state. I have the New Mexico, and I have all the different IDs, right? The petrol ID, the API number, all of those, all the metadata associated with that well. We have it here, right? So now with this metadata, now if you have hundreds of these wells, you have everything associated. So this is already QC'd. It tells you how good the record is. All of that is there, right? And the advantage is all the aliases, right? For example, the name, all of this information is all available here, right? So and there is a whole process of how we ingest. I'll go through that whole workflow, but I'm just showing you once the data is in OSDU, how you can do the query and all of those, and you can populate on the GIS map. Okay. So let us say you want to do a search, right? So here I can do a query here. So let me close this project. So now I can say, give me all the wells in the Eddy County. So because of the metadata, I can do a search. And it gives me all the data there. So this is my Eddy County here. So these are all my wells here. Okay, so, and here when I click that, that is where you see the metadata for the well. So all are interlinked here. So the lineage, everything is there. Okay. Now I can do basins, I can do all kinds of criteria there, right? Now, as you get more and more data, we can populate it here. Okay. So for example, I can say, give me all in Eddy County, all the wells that have gamma ray, right? I think it's slow right now. Let me see. Oh, there is a whole bunch of variations here. So, okay, with all of that, right? So it keeps updating. So I can look at all these different data sets. I can look for DT, like the density data. Right?
Does it allow you to transform an alias list or something like that, so you can
Yeah.
use a gamma ray for it's all.
Yeah. Yeah, I mean, there are many things we can build on this. There is a whole generative AI search we have, right? Again, based on the criteria that we have, we can build these things, right? These all configurable search. Right now, this is a JSON file that we can configure. And that is where we want to see what data you have and we can configure that, right? But essentially, what I'm saying is you can create a project for analysis and now you can build from there, right? So now it filtered about 42 logs based on this criteria. Right, you can create a project and visualize the data, right? So this is one simple example of how we took some public data, we populated it, and you're able to query and all this into the GIS system, right? So we can go through. Let me show you a seismic example, a seismic workflow. Okay. So these are all the steps of how you get the data into the seismic data into the platform. So as I mentioned, the cloud, I just skipped all my slides, but I'll show you one example here. So that is the ingestion workflow we have. So we have data in the cloud. So for example, let us say you have data on your hard drives. We have an agent that can run and populate into the cloud. So that way everything is in the cloud. So you can populate all of that and you can do a scan and run through it and it'll give you all the data. You can preview the data. Then we can process the data and we can ingest into this OSDU standard. It generates all this JSON manifest and all of that and gives you all the metadata and it's ingest into OSDU. Once it's there, you can now do the query just like how we did it and you can visualize the data, right? So there is a whole bunch of steps. Now, all of these are pipelines which I'll show you. I'll show you one seismic example how we do that and also for the well logs, okay? But for each data type, you follow the same approach, right? So just to give you an analogy, right? Like we are like the cargo ship, right? We take everything in bulk and we load as pipelines. And that's where the distributed computing comes into play. So when you have lots of data, we spin off new clusters and we process all the data and populate into the OSDU, into the platform, right? And then we'll do the analysis further. That's the next part. But I'm just showing you the data loading part at this point, okay? So let's look at the seismic workflow, right? So this is the cloud browser. So that is an AWS East one.
Sorry, can you share again? Sorry, can you switch the slide?
Oh, okay, okay, sorry, yeah. Well, I thought I shared the entire one, but I think it's disconnecting. Yeah?
I think it's when you do this presentation that you do.
Yeah.
It doesn't share, so I'm just opening the slides.
Okay, yeah.
Share first time here.
Yeah. So here, if you see, this is the cloud. It's just like your folder, right? And you have all the data sets here, right? Seismic data. We have a whole bunch of segway files here, right? And we have like here we have this drill caller. Here we have segway files. We have horizons and faults and all of those things. This is one of the horizon files. So essentially, it's like cloud. It's like a folder structure that you have, right? What we do is, once you load up, we do the scan of the entire data. Right now, we are scanning the entire data, right? And these are all the jobs. So when I run the scan, so you select this folder, right? And you give this file, and this is the path, and it scans all the data, and it basically gives you how good your where is the source, all of that. Okay, so now when I look at the source data summary, so now I have about 0.5 gigabyte, and then I have these files. So I can now click on the seismic, and I can do a preview. So it gives me the number of traces, it gives me the binary header and the textual header, right? I've not processed it yet. So I've just looked at the seismic header, right? So same thing with the well logs. I think I have to change the partition. So I'll come back to the well logs, okay? I'm just showing the seismic view. So here I can have 2D, 3D seismic and all of that. So what I've done right now is I've looked at my cloud browser, and then I'm scanning all the data, and I'm doing just a quick summary of my seismic header, okay? And now I will do how good is my seismic, right? So here I'm going to select one of the files, and this is the QC. This is the QC part I'm talking about, right? So before you do any kind of seismic attributes or all of that, we come up with a score, how good your data is, right? So it basically looks at your textual header, the binary header, right? And you have all the consistency. So as you were saying, right? So if you have all the seismic data, we can scan through all of this. And for each file, I can give you a score. The score is just a relative percentage of how good your data is. Like, does it pass all the 3D survey? Does it have the data formation, the survey type? And you can look at the geometry. Here it tells you it has the crossline azimuth, all of these things. And it gives you the coordinate system also, right? Here it says, I have the UTM zone, I have the datum, I have the UTM coordinates. So all of this, it is doing a scan, and it will give you, for each file, it gives you how good your data is. Okay. So if you see, I can pick any other seismic file, it gives you the summary of that. And then it gives me an entire seismic report. So it says I have 12 files, I have 95% data quality, right? Before you do anything. And this can be run on thousands of files. So as I said, like with TGS, we are processing almost close to a petabyte of data, right? So it's not so much on the number of files, but it's a lot of data, right? Some seismic files are 100 gigabytes. Like, for example, if you take the Poseidon files, the Australian data, right, which we are loading. So it's each one is about 100 gigabytes, each seismic file. So we process all of that. So before you do any kind of processing, this is what is telling you how good your seismic data is, right? So now, if you say 95% quality is good, we'll go ahead to do the further processing, right? Then one of the biggest challenge with seismic is the header, right? So the header is not standard, and we want to see the relationship between your inline and crossline, right? Now what we do here is we can select one of these files, right? And here is the header. Now this is the header, right? It has some, so we do automatic byte position detection, right? Now this is where the large language model comes into play. It takes this and it gives you the binary header. It extracts all this information, right? Textual information, and it has this byte positions. And now I can do a relationship here. So I can do the pattern now. So now my inline and crossline are aligning. So then that is my automatic byte positions. Because almost in seismic headers, they never put in the right byte position. They always have some other change in the header, right? So you'll never have it aligned, right? Now, let us say, so what the AI does right now is, let us say you have 1 million traces, it takes a chunk, it tries to find the relationship. If it doesn't find, it'll take the bigger chunk. So if you're doing the pre-stack processing, right, it will take more than 80,000 traces and try to look at the pattern, right? So now let us say I have 10,000 and do a search. Right now I have the pattern is continuing, right? Then I know that is my byte position. So that is how we are determining that. So if you have hundreds of these files, so this is where we are trying to save time so that when you have all these different files, we automatically detect the byte positions, right? Now, why is this important? So if you're most of the time, like dealing with SegWi is very painful. Let us say you have large, like 100 gigabytes, 200 gigabyte files. It is not optimized for fast I/O. So I can't query a specific trace and all of that, right? But now, with these byte positions, I can convert into the VDS format, which I mentioned earlier, the volume data store, which is cloud optimized. And I can do the fast query and look at my inline and crossline slices. Okay, so that is the next step, right? So now I've looked at all my seismic files. I've done a source data quality check. I said 95% is good. So now I'm looking at the headers. If the header is good, and I'm trying to automatically identify the byte positions. So then that becomes your header summary, right? So typically what happens is the big companies are creating what is called an exploration archive. So that is the seismic header summary. So essentially it tells me what is the bin header. So it has all this information here about all the different seismic data. So what kind of domain it is, time, depth domain, the file sizes, XY scalar, the text header, the latitude and longitude, the minimum amplitude, the sampling intervals, the number of samplings. It has all this information, right? So this becomes my exploration archive. Like for Oxy, they had 5 people doing this. I mean, they're all experienced geophysicists, right? So we saved them significant amount of time. What they do is they do the QC on this, on final QC, right? Again, it gives you 80% of the answer. sometimes you get multiple byte positions because the header is in multiple locations, right? So that's how we get this here, okay? Then we have this legal settings. We say, where does the data belong to, right? And seismic, they're even very particular, like for example, in Middle East, they don't want the data to leave, right? One small side note, this software we have deployed in Sao Paulo, in Brazil, in Petronas in Singapore region, and again in Abu Dhabi, right? So that the software has local regions because they don't want the data to cross the boundaries, right? And that is where AWS comes into play. So right now, we are doing some work for Petro Vietnam. They don't even have a data center, right? And they want all the data to be in country. So this software is running on they have a rack, which is called Outpost. So you can put it there. And it connects via satellite. So that is how the same software is deployed in multiple regions without violating the data privacy issues, right? I didn't go into deep into the data privacy issues, but there is a whole bunch of governance which talks about data groups, service groups. It's all too much IT stuff. I skipped all that. But essentially, all the policies are well defined, right? So if you just look at the governance here, so these are all the different groups, the data groups, owners, all of those. There's a whole bunch of definitions that they have, the policies and everything. Owners, who is the owner and all that. So you can control who has access to what data in the platform, right? And this one is defined by the standard. We didn't come up with this. It's a standard, we have just adopted that, okay? Then we go to this whole seismic ingestion, right? So here you can select the bunch of segway files. We can run through the ingestion like this. We can run and select all this. So here is where people have been running the jobs here, the seismic ingestion, all of this. So this is again the different runs. So here I processed 8 files. Everything is processed. Here we can see each file that was successful. So this is what I'm talking about, the distributed computing, right? I'm processing 8 files at the same time in 2 minutes, right? It's like that. Now in the platform, once you get access, right, you can run through all these, you can ingest and play around. So each one will have a workspace that you can play around with, right? We'll walk you through all of that. Okay, and then we have the seismic sub-project. What does this mean, right? So just to quickly give you, the seismic sub-project is essentially, let us say you take Shell, for example. Like they have one in London, the data center is in Ireland, and they have one in Houston. They don't want people to be accessing the data. So each one is a sub-project, and they have control permissions on that, right? So that is how it's all more like access control. That's all it is. And here, for example, here we have all this, like this is one of the Poseidon files, right? So that is the 100 GB file. So these are all public data, by the way. So if you go and search the wiki page of Segway, the Poseidon Australian data is there. So it's about 100 gigabytes. So the good thing is you can play around with all of that and you can do this, right? So what I'm trying to show you is that 100 gigabytes of Segway file is converted with the VDS format, which is cloud optimized. So I'll show you in a minute how you can query the data, okay? And the same thing, now you can do the metadata search. So I can search for the seismic. So this is all the seismic trace data, right? So you can look at this, just like how I have the wells, now I have the header for the seismic itself, okay? And then we have the data quality, and this is what I'm talking about, the data quality aspect, right? So the previous one, we looked at the seismic data quality, like before it was ingested. Now we are looking at the data quality for all the data sets here. So it tells you, does it have all the mandatory attributes? Does it conform to the data? Does it have all the descriptions? Does it have the entitlements and obligations, all of that? So these are all the compliance as per the standard, right? Like for example, right now we are doing some work for Petrobras. So their mandate is we ingest the data and it should be consumable by Petrel, OpenWorks, all this Schlumberger Halliburton software, and that uniform policy is governed by that, right? So that's right. Okay, and then we can look at the visualization. So here I'm looking at the 2D slice. Right, and this is my histogram. So I can do the histogram here, and I'm applying my seismic data, right? Again, this is very dense, not so much, this is all test data sets, right? So I can now look at the inline, crossline, the crossline data, the crossline plane, and then I can look at the depth slice, right? I can change the depth slice, right? So right now, what am I doing, right? Because it's converted into the VDS format, you can see the response I'm able to query quickly. I can slice and dice individual traces. I can do the depth plane, all of that, right? So that is the whole idea here, right? So that is where you have the level of detail, all these concepts. So I'm now going through 2,200 feet, and I'm updating the seismic slice, all of that, right? Again, this is all happening in the cloud with the VDS API, right? Now, TGS is using something similar, format called MDIO. So they have the data universe. So the good thing with this one is I can go and look at any bin grid. I can pick a specific seismic slice and say, I want you to give me this exact inline and crossline, the depth and all of that, right? So we can exactly pinpoint the data, and all these formats are optimized for faster IO, right? Now, this will enable the machine learning workflow, right? Like the whole idea is if I can get access without downsampling, I can do the more higher resolution, like the detection of the geobodies and all of that. And then I can apply different, like all of this is the Petrel scale. Like if you want to, you can apply different color maps. You can look at all of these. You can do different smoothing. You can increase all of this. So these are all the different parameters that you can slice and dice the seismic data, right? And then I can look at the 3D view. So now I can migrate to the slice and go to the seismic slice. Right? All of these is because of the VDS format. So I'm able to quickly slice and dice through exact data, right? And I can do different sampling. Like here, I'm doing level of detail 3. So what does level of detail mean, right? So there is only so much you can see visually with your eye, right? When you have large amounts of data, you apply the automatic downsampling so that you can see the actual resolution of the data, right? Now, all of these formats are optimized for cloud. So when I use seismic, the VDS format, I can quickly navigate through exact inline and crossline and query the data, right? So this is the typical workflow. Now I can do other seismic attributes and all of that. But what I mentioned here is you took the raw data, you went through a bunch of steps doing the source data quality. You're looking at the header analysis, identifying all of that. Now from here, I can do any kind of computation. I can do seismic attributes and all of that. And that's what you were mentioning. If you have all the data, I can load it. This is centrally available in the cloud, right? And there is no limit of how much you can store, right? Like a typical, the seismic bucket can hold up to 4 petabytes of data. So that means you have a big seismic store, and then you can create more replicas of that, right? So again, these all centrally located. you can access the data, all of that. Okay.
So use this to sort of view all your data sets, or would you use it to, like, if you wanted to pull attributes or something, should you do that in here, or we should do that in whatever your software is, and then turn that to?
Yeah. So good point, right? So that was the next aspect here, which is extracting the attributes along this, right? So typically it is done in our OSDU, another framework. Right now I was just focusing on the view. So here is where you can extract properties along the well path like this, and then you can extract along the surfaces and faults. And then you can extract Z maps like this from that. So you can extract attributes like all the, essentially against any geobody, you can apply and extract the information. Okay. To answer your question, it's a separate workflow, not in the software, but it's, yeah, I think we can link it to that, but it's in a separate workflow. Okay. Right now, what I'm showing you in the PIEScale is the data management, but as a DO where you have a separate workflow of that. Okay.
Sorry, could you share again? I think every time we switch
Oh.
on the slide, but
Oh, good. Okay.
this is the-
So any questions so far?
If you were loading.
Yeah.
Several terabytes of seismic data.
Uh-huh.
And it gives you a score. Or if your score is greater than 90%, do you tell it, go ahead and ingest? Or if it's say it was 70%, is it, that's not good and you stop?
Yeah.
And you see the data and then ingest?
Yeah.
Or
So
where do you start and stop?
there are two things, right? One is the overall health of your data, of all the seismic data, but then you're ingesting one record at a time, like individual one, right? So let us say you have a large block, only certain blocks have problems, right? So those will have a lower score. So overall score might be less, but you go to the individual score. We say across for each one, you say 90% and above you ingest. Anything less than that, you stop, right? And there is also some fundamental things, right? So for example, if the EPSG is not defined, you stop because you don't know where your coordinate system is. There is some fundamental requirement that you want to do before you do that. So it need not be 90%. It could be 80% or 70%, depending on what you want to do. But fundamentally, we look for the location, we look for the headers as much as possible. Like, for example, description is relative, it's only 5%, right? So we don't enforce so much on that, right? Especially for seismic, again, based on the data type, right? Supposing if you're looking at well logs, we absolutely want the UWI, all those things, the curve names, the units and all of that. If not, you'll stop. But sometimes we have seen the mnemonics are like really crazy. So they don't have, like they put C, which could be, concentration, it could be centigrade. They have some strange mnemonics. So in that case, we just stop it, but we let the other curves to be ingested. So it depends on the situation, but in most cases, as long as it has decent header, location, units, description, the metadata, fundamental things are required. For wells, like location is again very important, UWI, and then associated information, right? Sometimes they don't have the basin information. The good thing is you can always enhance the metadata. So it depends on the threshold, how much data you have access to. Sometimes if somebody is doing a individual analysis, they may not have access to all the other information. Like for example, the lot number, the play, all they have some unique IDs. You may not have access to that, right? Sometimes when you're doing just a field level analysis, you may not have access to trajectory. So it depends on the need. But in most cases, for anything, if the basic metadata is not there, we stop. Either you correct it. There are situations where, for example, in the well, there are a lot of missing data. So one is the metadata correction, other one is the data correction itself, right? If there is missing data, then technically it is possible to ingest and say there is still missing data, or you can correct the missing data, fill the gaps and ingest, right? So in most cases, people want us to fix the metadata.
So if you have a customer.
Yeah.
And they have many terabytes of data, and they give you an external hard drive with
Mhm.
X amount of terabytes of data.
Yeah.
It's still faster for you to run your agent.
Yeah.
Correct? And just find out what is
We
this.
tell them how good the data is.
Because
Yeah.
you could have a technician going through there
Yeah.
and checking headers, but that could take
Yeah.
years, right? Your first step of an early step is to have your agent just
Yeah.
scan everything and let's see where we are.
Yeah.
And if it's greater than 89%, we could probably just go ahead and just.
Yeah. And if you saw in the seismic source data quality, right, we exactly pinpoint, like here, sorry. For each file, we exactly pinpoint what is wrong with the data. Let me see. Yeah. I think I just need to log out and log in. Yeah. Yeah, we exactly pinpoint which file has what problems. Whether it's the coordinate reference system or is the header system, is it missing the EPSG or is it the geometry is problematic? So all of that we pinpoint. So, for example, as I said, like in Oxy, there are like 5 people doing this. So we reduce the time to do the initial QC. Okay. Start to log out once. Yeah. Yeah.
So while you're doing this, maybe you're getting a seems great for, big data management and stuff like that. I'm trying to figure out the use case for like a small company to, maybe like I said, maybe you're getting like more like as an interpreter, for the person.
Yeah. So it is the prospect.
Oh, okay, perfect.
So small costs and those are machine. Right now, so
Oh, okay, perfect.
Once you have the data in the cloud, and if you're small, 1,000 wells, you can reduce your AWS footprint, right? In other words, it's less. Yeah, so if you need to increase it, if you make an acquisition. But if you're small, 100 wells or down, it's probably less money.
Yeah.
Your contract.
The storage, we have been enforced from. What's the data is? Cold storage is that 90% less. So typically, we have like 10 probably like $2,000 for the whole thing. You still reduce the cost of sharing all of them. I think the way to get the overall cost, maybe you can probably smart. So you can easily scale up, and there are a lot of incentives. We put everything in post. Like we are working with this type of. They have 50 developers on. So they want to keep one of the active. You see, now they want to. So that is the default ratio. So the course will be 90% cheap, right? And if you want that, it's just what so cloud is good and bad. Good in the sense that there is speed. Bad if you don't manage the cost properly or if you don't do it properly. So most people put it in the executing second cost. So that is the calculate performance. For the small players,
Okay. But couldn't you make an argument that like if I had 10 silent surveys, the hardware is a heck of a lot cheaper than the cloud first over?
yeah. So it's easier.
Yeah.
So yeah, we always like for example, something let's say I can have the IDX in some you can scale. It's a balance.
Yeah.
But what we are seeing is here only 7. We spend lots on the cloud, then we would have started the cloud.
Okay.
All you have is that is the same. Others are very confident. So I think that's done.
Okay.
You should, yeah.
Yeah.
So, yes.
This long. He's holding the capital. I know.
They also played this kind of I said it's right. It's some ratings and injunction. Yes. Still. The key live without me. I'm not going to find out. Just down the farmer gets claws on the
Yeah. So here is an example of the geomechanical model, right? So what we are looking at is we have some input data and we are doing the rock properties calculations here, right? So once the data is loaded, I'm able to access the raw data, and then I'm calculating all the Young's modulus, internal friction, all of these here, right? And then I can do some vertical stress calculation right from the density. I think I don't know why it's not calculating here.
This is logs or silent?
These are logs, yeah. So right now, what we're doing is here I'm looking at the stability of the well, right? And I'm calculating whether there is a breakout or not, right? So here we are looking at all the inputs. In this case, there is no breakout, but you could have a breakout or the tensile strength, right? So on a depth by depth basis, you're doing the calculation here. Now, what we are trying to do as part of the drilling risk assessment, right? We are taking the input logs. We are calculating the rock properties, the vertical stress, the formation pressures, and all of that. And ultimately, we are saying at this given depth, whether it is a breakout or a washout. Based on that, you can kind of quantifying your stability of the well, right? From the geomechanics point of view, right? Let me show you. So this is a suitability engine that we've created. Again, there are many ways to quantify your suitability, right? So what is a suitability model, right? Essentially, what we are saying is it's a quick way of quantifying once you have done all your different kinds of analysis, like, the seal integrity, the reservoir quality, all of that, and the economics. Given all of this as a quick identification of your prospect, can you give me the drilling suitability index? Like, should I go ahead and drill the well or not, right? This is not replacing any of the modeling capabilities, right? You still have to have the petrol model, all of that. But after that, if you're a finance guy and you're saying, I'm going to put my bets in the next play, what are the things that you need to take into account before you say this is a go, no go well kind of thing, right? So that's what the suitability model is. Now here you can select, the scoop versus stack and conventional. You first select the play, right? And then you give all the different criteria here, the maturity, the reservoir quality, all of that, the trap positions and all of that. And here is where you're saying my well is, say, 600,000, and my depth target is 12,000. My net pay zone is 5 feet, all of that, right? And then based on that, you're now, again, you want ultimately tied to the money side, right? So you want to get the price of oil, and then you give all these different aspects, right? And then you go do the suitability evaluation, right? And then it gives you a score saying that, like, this is your net present value of the well, and this is your break even. And this is how based on that, I'm going to say the reservoir quality is okay, but the remaining parameters are not allowing you to go ahead and drill this well, right? Now, let us say I increase my pay zone. So let us say I increase it to the oil price, and then I increase the pay zone here, right? And I increase the porosity to, say, 35%, right? And then I run my suitability model again, right? It's still no go. Yeah, so these are the criterias. You can play around with that and determine. This is a quick evaluation of the data, right? Yeah. Go ahead. Sir.
So jump back up to the top.
Yeah.
Did you set your
Go ahead.
so are you setting your parameters in here, or are you pulling that threat data that you?
Yeah, in this case, right, this is, I'm setting the parameters right now, right? But ideally, you will get it from the model. So this is a framework at this point, right? I'm not saying we have done this analysis. This is a methodology of because how did this come into play, right? So when we were talking to all the different prospect people who are actually in the business of selling and buying acreage, they said, like, we have all these analysis, but we cannot put it all together to do a quick assessment, right? So that is the whole idea with this, right? So now if I can do different interpretation and I can change my quality index and all of this, and then I can run suitability again, right? So now it is marginal, right? So it improved the score, but it still says you need to get, it gives you some, again, this is not something that we generated. So this is where the model, the large language model, based on these criteria, it is suggesting based on the public knowledge, right? Now, this is in no way replacing the modeling, right? This is giving you just a benchmark of where to look for all of this, right? Now, there are many ways to do suitability model. This is one methodology. Like, there are a lot of other things that you can do. Like, we can go deeper into, like, for example, the economics model. Like, this is where we are partnering with S&P Global, and they have a whole bunch of parameters that we can do it, right? Yeah.
So can you ask me, like, run with quality or something, like, how did you ride it, right?
At this one?
Yeah, like that. Yeah, what are you? I think we jumped from like one end of the workload to the other end.
Yeah. So good point, right? So right now, this one is a methodology, right? Reservoir quality model, we are not doing it. We are taking it as an input. Each one is a detailed analysis that you're doing outside, not in the software itself, right?
So what kind of data went into that reservoir qualities?
So there are two things, right? The one is the permeability and porosity, how good the decline, like the reservoir pressure and the permeability and the porosity and the skin damage around the wellbore, all of that went into account, right? And also at what phase you are in terms of is the well producing over 18 months, or is it is it unconventional, all of that. So those go into the reservoir quality of that. Okay.
So can you back up a little bit, like,
Yeah.
Presumably at some time.
Yeah.
Have enough information, you can turn these subjective criteria.
Yeah.
To objective criteria that you calculate.
Yeah.
That point is not met. You haven't done that yet here. And will you be able to do that in the future?
There are a few things, like, for example, the stack pay potential, we don't do that, right? So primarily we are focusing on the seismic confidence and the overpressure. Those are the two areas that we are doing deeper modeling. The remaining, we are expecting others to provide the information.
right, so what data is this looking at to come up with these scores? Like, did you put in a thickness grid and a porosity grid and a permeability grid or something, and that's what it's.
Yeah, so from your standpoint, right, these look like, a bunch of numbers that we are making it up. The point I'm trying to make here is, like, for example, when you're doing the completion, the pay zone, the height, right? So this is coming from the completion information, like where are you perforating and all of that, right? So that is where your net pay zone is. The depth of the well, the economics of the well, right? And the closure area is typically you're looking at how much is the net potential coverage, right? The porosity, all of this is coming from the reservoir properties, right? So this is actually coming from the reservoir properties. And the same thing is tied to the quality, like how good is your confidence on that, right? Now, the overpressure and the seismic confidence is what we are looking at, how good the seismic quality of the data is. So those are the two areas, right? Now, the maturity is subjective, as he mentioned, right? The trap seal and the stack potential is also subjective. Again, those are the things that are going into the economics aspect of it.
But presumably, if you're reading the reports that you have
Yeah.
in your database of maturation studies, and you can come up with a more objective number than
Yeah.
just saying 4.
I agree. Yeah.
You're not there yet, but you
Yeah.
could be there.
Yeah.
Not tomorrow. Today.
Yeah. And as I said, like, we came up with this approach as a first pass, right? There are many things, like even within the economics, there are a lot of different criteria you can go into that, right? But right now, what we are trying to do is come up with a methodology to qualify your overall aspects. And as you said, like, if you had access to all those reports, we can populate most of this. Right now, most of the reporting we are getting is the things that we have under control is from the reservoir physics. These are under control because these are the things right? All others are subjective. Like seismic, you have control. These are, I think, from the reports and all of that. Yeah.
So there's multiple softwares that kind of, areas and that run economics and do all this.
Yeah.
What's the selling point to switching to this?
What we are trying to do is combine your interpretation to economics, right? There are people that are doing only economics. There are people that are doing all of this, right? So the bigger value prop is we are creating one platform for everything. So for data loading, for documents, for interpretation, and this kind of analysis, right? Again, there are many things you can do, but mainly from the drilling risk point of view, we looked at the geomechanics. We look at the seismic. So those are the two areas we have confidence in. So seismic will give you where is the location, we have the property extraction, those three things, right? And then the economics is where we have to rely on the reports or S&P Global, where we have a direct API. Because most of the economics are given either by Enverus or IHS or S&P Global, right? So we have to rely on them to give us the economic information. Now, if they don't give us that, that is where we are giving you an option to play with the parameters, right? Because the capital expenditure, you don't have access directly, right? How much money has been spent, I don't think it's public knowledge. So then how do you quantify the economics of that, right? Either you have to rely from them or you have a mechanism to do that, right? All this methodology, we keep it very open, how we come up with these weighted scores and all of that, right? So one thing we are improving is the sensitivity analysis, which we have not done, which we have not released yet. We do a Monte Carlo simulation of giving you which variable is actually affecting your final go, no go, right? Now, what we are trying to do is a framework. I will share the actual algorithm. This is all public knowledge. We actually got this from a paper, right? So all of this quality scoring and all that, there is a clear paper. I can show you all the methodology of all of that. But the idea is these weights, again, we have to rely on, some are subjective, we have to rely on the reports or somebody has to input that. But the methodology is pretty open in terms of how we are coming up with these numbers, so.
Can we maybe jump back to the interpretation side of things and how that's kind of straight into economics? I think that's maybe.
Yeah.
So in geomechanics,
Yeah.
there's only one model that you use to calculate the varying rock mechanics properties based on level.
Yeah.
Is that correct?
Yeah.
But there are other items that have multiple models.
Yeah.
You calculate all models or choose a model or black box.
So right now, for the failure criteria, we have this more Coulomb and Lade. There are specific models that we are using. For formation pressures, we have those, right?
But you would put that up there.
Yeah. Yeah. So all these are from the public literature, right? Like McNally, all these models are from the public literature.
Proprietary model.
Yes. Yeah. So this was actually a desktop software that we developed with Repsol over last 8 years, and it was actually used over 300 wells. So I'll show you all the criteria that went in. So these are all the different models you have for sandstone, for shale, all this. For all the different Young's modules, there is a whole bunch of published literature that we use, all of this. Yeah, for all the different rock types, we have a whole bunch of equations. So now this desktop software has migrated to the cloud. But essentially, these are all the different equations. We have the drilling reports, all the different things that go into this whole modeling of that. Okay, so here we have the typical days versus depth and all that. So I just showed you just a small sequence of it, right? Then you can do the collapse pressure. You have the depth stretching, all those like very detailed modeling we can do. We have sanding effects and all those things, right? So the big picture, what I'm trying to make is there is detailed analysis which you are not replacing with the AI effect. holistically, how do we put it together is the framework that we have created. So the whole mechanism of ingestion, data quality is one aspect. The second aspect is once you have all of these, we are bringing in the modeling, the whole geomechanical modeling for the risk assessment. And then there is also a flow model that we have for the inflow and outflow. And then once you have that, we take the reservoir properties and we have given you the suitability model framework, right? Now, there are like 4 or 5 different suitability models that you can apply. I'll be happy to share that thing. Again, all of these are like abstract models that needs the data to be fed in, right? So, but the methodology is pretty standard. We didn't invent that method. It's pretty standard methodology. So.
And so is this as simple as like, I'm just uploading some logs and it's running for me all these, these things?
Yeah. So right now I was just showing you individual aspect. So essentially this desktop software was running independent. So for example, if you don't have the logs, we can fill in the seismic and do a prospect plan, right? We can take the seismic log as your sonic, and then I can do all the other calculations from that, right? So this was running in a siloed environment. We took that, we put it in the cloud. Now we can contextualize everything, right? So, and then, yeah, so that is the whole idea. So at this point, what I plan to do is we'll give you the software. Now, all the clicking and everything, there are like videos that you can play around with it, right? Any data that you want us to load that is publicly accessible, just let us know. We can load it up into there is no fee for you to use the software. And any gaps that you've identified, like those kind of reports and all those things, right? How the number came in. So I'll be happy to share the suitability, the actual methodology, how these weights apply, right? And also the different variants of it. We have been talking to S&P Global about how they do the economic evaluation, at least the numbers that go in the NPV, how they come up with the NPV of the well and all that. What we are trying to bring in is the cost aspect to the scientific analysis. Like, for example, the drilling report, most of the time you don't know how much it has actually costed to drill the well, other than an abstract number, right? So we are also bringing in the torque, all the drilling parameters, like the MSC calculates, all those things we are bringing in here, right? So right now, the goal is twofolds. One is with respect to how good the well is, like can you reach? We are looking at 2 aspects: the stability of the well and the economics of the well with the seismic. Now, is that sufficient? Probably not. We need to do more. That is where we need to get more flow modeling into play. We have the tool, but again, it's only giving you a steady state interpretation. It's not continuous updates. So if you get a spin meter reading from a daily production rate, then we can quantify to see if the production is declining or all of that, right? But we don't have the daily production rates. We don't have access. So whatever modeling we do, it's only steady state, which is not a good characteristic of the flow, right? So that's why I don't know how much of the daily production rates you get from these wells. So if you want to do that, right? Again, you're only doing prospecting at this rate. So the only reservoir quality would be like, is the production declining? And what is the rate of decline, right? Then you can say, okay, in the first 18 months, I have high chances of getting it, or the production is rapidly declining, then that is not a prospect location, right? So it's highly subjective, the reservoir quality. Especially in the unconventional, suddenly you see a drop in production, right? So how do you qualify that, right? That's why we gave the reservoir quality as an index. So how much of data, maybe during lunch we can discuss, right? Where we don't have enough experience is how much of public data that the state is collecting, right? How much of it is accessible? And is there a way we can work with the state? Because it is supposed to be public data, right? Yeah. Yeah. Because that's what me and Susan, we are trying to see, because we are not going to charge for the data. We are not reselling the data, right? What we are trying to do is resell the, like monetize the interpretation, right? So
I'm gonna, let's stop it there, but, we got one kid next to, so we're gonna find a solution. But, yeah, thank you for coming.
yeah, just one thing. Like I said, like everything else, we all have access to this for experience. Then our technical team will help you. So for example, what we're trying to get is all the public data, like the pods, geobody, whatever is available will be loaded up. You can play around, you can critique what you like, what you don't like it, and how we can improve. The goal is to see leverage any public data to better understand, right? What possible, right? The positive exercise is that then I will share all the modeling aspect of geomechanics, the risk modeling, the flow modeling, and as well as the swift fixed modeling. So there is nothing black box in the software, it's open. And the good thing is there is no limit of how much you can do. Because we have till that kind of arrangement there, so we can load as much as we want. And we are now trying to load, I said like we have finished the Brazilian asset. Because there it has all kinds of information publicly available. So we thought that is the first step. So they have all the way from post samples to all the way to crops, the lithology, everything is there publicly available. Shared file.
Do you have a data set?
Yes, yes.
Okay.
So right now I was trying to synthesize everything. So the Brazilian data, you can play around, but it's the same concept, right? You can play around with it. And there's a lot of information. So we have all that. And then we have some from Guyana that is open. The Exxon is they have like a few wells there. Slowly the public.
Thank you.
Thanks. Thank you. Oh.
But thank you. Yes, please stick around and talk to everybody. We'll connect via email.
Yeah, yeah.
Awesome. Thanks, yeah.